Right. So I'm very glad to present David Soudry, who will speak from Tel Aviv University. He will speak about his joint work with David Ginzburg on double descent. Please.
Okay, thank you very much. So let me start with the generic descent. It will show how the method works, but we also need it for the double descent. So in this talk, F is a number field and A is its ring of Adels. And I start with an irreducible self-dual cuspidal representation tau of GLK Adels. And for simplicity, I assume that it has a trivial central character. So tau is given, and we start with tau. So with David Ginzburg and Steve Rallis, we constructed, now it's some 20 years ago already, an explicit way, irreducible automorphic cuspidal representations pi of an appropriate split group, G, according to the Langlands functoriality, which leads to tau. And what was special about these representations, that they had the extra property that they are also generic. So G is a split classical group, which on which the representation pi lives and lifts to tau. And we used our method of automorphic descent. We also took care of double covers of symplectic groups on GL2N with the requirement that tau is such that the exterior square function has a pole at 1 and the L value at 1/2 is non-zero, as well as cases of quasi-split even orthogonal groups and quasi-split unitary groups. And then there is a modification about the requirement on the central character. So let me review the construction in the example of a split odd orthogonal group, SO2n plus 1, which I realized as written here, transpose G times the matrix W2n plus 1, this is WR, times G equals W2n plus 1. So now we require the tau is cuspidal on GL2n, so K is 2n, and we require that the exterior square function of tau has a pole at S equals 1. So the construction is this. We consider the Eisenstein series on SO4n, split SO4n, induced from this parabolic subgroup Q2n, which has Levy part isomorphic to GL2n. You take tau on the Levy part on GL2n, multiply by the absolute value of determinant to the power S. So this is the parabolic induction, and you take an Eisenstein series corresponding to it. It has a pole at S equals 1/2 when you vary the sections. This is because of the requirement that the exterior square function has a pole at S equals 1. You consider the residue at S equals 1/2 of this Eisenstein series, and you apply to it a certain Fourier coefficient with respect to a character, which I denote psi with index, which is the subgroup, the unipotent radical which I denote U with index 1 repeated n-1 times. So here it is, the Fourier coefficient along this unipotent radical. And what is this unipotent radical? It is the one of the standard parabolic subgroup, which I denote by Q with the same index, inside SO for M, so that the Levy part, M with the same index, is isomorphic to GL1 cross GL1 n-1 times SO2 n plus 2. And the elements of this unipotent radical are written here in this matrix. And Z is an upper unipotent n-1 by n-1 matrix. The character C sub Z n-1 is this Whittaker character written here. You just take the sum of the second upper diagonal and substitute it in a given character, additive character psi. And then you have this part of the character written here. So we take the Fourier coefficient exactly with respect to this character along the unipotent radical U with index 1 to the power, let's say, n-1. And when you examine the connected part of the stabilizer of this character inside the Levy part, you get this subgroup D. So you see that it is isomorphic to the subgroup of SO2 n plus 2 of elements which preserve this anisotropic vector, this one written here. So it is isomorphic to SO2 n plus 1. So let me write or denote by T an isomorphism from SO2 n plus 1 to D. And now this is the definition of the descent of the representation tau that we started with to the group SO2 n plus 1. We simply take the space generated by these functions, the Fourier coefficients above of the residual Eisenstein series at S equals 1/2, restricted to the stabilizer, the subgroup of the TG. So this is an automorphic representation of SO2 n plus 1. And there is a similar definition of the descent tau for the other cases. Say when the symmetrical function has a pole at S equals 1, or the acyl function has a pole at S equals 1. And the main theorem on the descent with Ginzburg and Rallis is first that this is a non-vanishing space. Second, this is a cuspidal space. It consists of cuspidal functions. It is a cuspidal representation. And therefore, it breaks into a direct sum of irreducible cuspidal representation. This direct sum is multiplicity free. Each irreducible summand is generic with respect to a compatible Whittaker character and lifts to tau. And any irreducible automorphic cuspidal generic with respect to the same character as should be in 3, pi of the group GA. So now in this example, this is SO2 n plus 1, which lifts to tau. You can see it inside the descent, inside deep psi tau. That is the complex conjugate of pi has a non-trivial L2 pairing with a descent. So a remark is that in most cases, this descent is actually irreducible. In the cases of SO2 n plus 1 and the metaplectic group of SP2N, this is work with Diwa-Jang. And for quasi-split even unitary groups, Morimoto proved it. It should be also irreducible for symplectic groups, but for even orthogonal groups, no. Let me stay with the example of SO2n plus 1. Just briefly, what is the idea behind the construction of the descent? So the idea is that for any irreducible cuspidal generic pi on the group on SO2n plus 1, when you consider the integral, of a cusp form inside the representation pi against the same Fourier coefficient of the same Eisenstein series, but now take any complex number s, not just the residue at s equals 1/2. This integral is one of the Rankin-Selberg integrals for the group SO2n plus 1 times GL2n. But you need pi to be generic because otherwise this integral is identically 0. So this integral unfolds to an Eulerian integral, and it depends on the Whittaker, certain Whittaker coefficients of the cusp form phi pi. And you can compute the local integrals almost everywhere where all data is unramified and get this ratio of partial L functions. The L function of pi times tau at s plus 1/2 divided by the partial L function, exterior square L function of tau at 2s plus 1. This comes from the normalizing factor of the Eisenstein series. And then there is a finite product of the local integrals, which can be controlled. You can substitute data and make each local integral holomorphic and non-zero at a given point. So if I take pi, which lifts to tau, then of course the L function, say partial L function of pi times tau at s has a pole at s equals 1 because it is equal to the partial L function of tau times tau dual. Tau is self-dual. So therefore, this ratio of L function here has a pole at s equals 1/2. The denominator at s equals 1/2 is this exterior square L function at 2. It's non-zero. So the pole remains. And when you go back to the Rankin-Selberg integral, because you can control the local integrals at the finite set of places, you see that the global integral has a pole at s equals 1/2 when you substitute appropriate data, of course. So where does the pole come from? It comes from the Eisenstein series. So therefore, the integral of the cusp form phi pi against this Fourier coefficient of our Eisenstein, of the residue of the Eisenstein series, is not identically 0. And this means that pi pairs in the sense of this integration against the descent. So every pi which lifts to tau pairs against the descent. And conversely, if pi pairs against the descent, the theorem GRS that I quoted before tells you in particular that pi is, say, isomorphic to one of the summands of the descent, and therefore it lifts to tau. So as a remark, just let me say that, of course, these Rankin-Selberg integrals are not limited just to SO2n plus 1 and GL2n. You can take instead of GL2n any k, GLK, and similarly for other split or quasi-split classical groups. Now, so this was an introduction. Our goal is to find explicitly all irreducible cuspidal pi on GA, generic or not, which lift to tau. And for this, we will consider the descent that you can construct, derive from the generalized doubling method of Chi, Friedberg, Ginzburg, and Kaplan. So let me recall the generalized doubling method. So I switch example just to show you that you can choose any classical group. So split for this talk. G will be SPM, and M is an even number, so M over 2 is M prime. Take any two irreducible cuspidal, representations of GA, so the symplectic group in this example, pi, and tau on GLK. And the generalized doubling method provides global integrals which are Eulerian and represent the L function of the pair of representations pi and tau at S plus 1/2. And now there is no restriction on the representation pi. It doesn't need to be generic or have any model. And this generalized the doubling method of Piatetski-Shapiro and Rallis, which worked for tau characters of GL1 for k equals 1. So what are the ingredients? Similar to before, you need an Eisenstein series on a larger group, which involves the given tau on GLK. You need a certain Fourier coefficient applied to this Eisenstein series. And we want it to be stabilized by the group G. And certainly the cusp forms of the cuspidal representation pi. So let me review the ingredients. The Eisenstein series lives on the bigger group H, which is SP2KM. Okay, K, the representation tau was on GLK. The representation pi was on SPM. M is an even number. So you take this big number, 2KM. And it corresponds to the parabolic induction from the Ziegel parabolic subgroup, which I denote by QKM. So the Levy part is isomorphic to GLKM. And on the Levy part, you take the Speh representation, delta tau M, the Speh representation of GLKM, say of length M corresponding to tau. So it is realized by the residual Eisenstein series on GLKM, which corresponds to this parabolic induction here. You take tau, repeat it M times, but with decreasing powers of absolute value of determinant, starting with M minus 1 over 2, and you decrease by 1 each time until you get to 1 minus M over 2. So I denote such an Eisenstein series by E. The section I denoted F with index delta tau M and the complex variable S. What about the Fourier coefficient? It is along the unipotent radical, which I denote by U with index M to the K minus 1. It is the unipotent radical of the parabolic subgroup with the same index, but I call it Q, so that the Levy part is GLM times itself K minus 1 times SP2M. And the character, let me just say that it is stabilized by a subgroup of the Levy part, which is isomorphic to G cross G, to SPM cross SPM. And the stabilizer or the embedding of G cross G looks like this. you take a pair G and H in G, SPM, with Adel coordinates, and you take a block diagonal matrix, which looks like this. You repeat G along the diagonal K minus 1 times. This goes together with G star, repeated K minus 1 times. And in the middle, you have the direct sum embedding of SPM cross SPM inside SP2M. So you can realize it as follows. Write G as a 2 by 2 block matrix of M prime by M prime matrices G1, G2, G3, G4. Put them in the corners here and put H in the middle here. This is the stabilizer of the character. And now write this Fourier coefficient. And of course, it is, and denote by TGH, yeah, the embedding, this embedding of G cross G inside SP2KM, inside H. And the Fourier coefficient becomes naturally an automorphic function on GA cross GA by this formula. So if you want some more details to explicate the character, it is enough to, because it is trivial on the commutator, I can say that if you take the quotient of the unipotent radical um to the k minus 1 by the commutator, it is, you can parameterize it by this vector of matrices, k minus 2 matrices, which are m by m, x1 up to k minus 2, and y, which is m by 2m. You take the sum of traces of x1, x2 up to xk minus 2 and substitute it in a fixed given non-trivial character psi of the Adel's trivial on F. And also we need to add some partial trace of this last matrix Y, and it is trace of Y times A, and here is A. So we have this Fourier coefficient, which is a function of on G cross G, GA cross GA. And now we integrate it against the product of two cusp forms, phi pi G coming from a cuspidal representation pi, and phi sigma H coming from a cuspidal representation sigma, both irreducible. So here it is. And this is the global integral that that Kai, Friedberg, and Ginzburg and Kaplan found out, generalizing the doubling method for real S large enough. You can see that it is an Eulerian integral. So let me review the ingredients which appear here in this adelic integral. At least in this integral, you see that the integration is over Adel points. You don't have to divide by any rational points. So let me start with this function C of phi pi, comma, sigma H of phi sigma. This is almost the inner product, L2 inner product of phi pi and sigma H phi sigma with some modification. So here it is. This is the integration of GA along GA modulo GF of phi pi G times. So here we have the right translation of phi sigma by H. And instead of G, you have G iota, which is an outer conjugation by this element. This element does not lie in the symplectic group, but in G SP with the similitude factor -1. And for the rest, delta 0 is some certain element which is a certain representative of a double coset, which survives the unfolding in HF with rational coordinates. And the upper psi here means that we take a Fourier coefficient on the Speh representation. So this is the composition of the section with the Fourier coefficient on the Speh representation with respect to a character, again, along a unipotent radical inside GLMK, which I denote by V with index M to the K, and here it is. This is the unipotent radical, and you take psi of the sum of traces of the matrices x1 up to xk minus 1 in the second upper diagonal. So this defines a functional on the Speh representation. You know, you can think of it as a generalization of the Whittaker functional of Whittaker coefficient if you take m equals 1 here. And the uniqueness was proved in general by Kai, Friedberg, and Kaplan in the paper where they do the local theory of the generalized doubling integrals, which resulted in this fantastic proof of the existence of the functorial lifting, you know, without trace formula. So recall this bilinear pairing, which appears as in the integrand when we unfold the doubling integral to a product to an Eulerian integral. So it was almost like the L2 pairing. So if you want to, so first, for it to be non-zero, certainly we need pi to be isomorphic to the conjugate of sigma composed with this outer conjugation iota. And otherwise, the global integral would be 0. So for sigma, you essentially need to take pi up to this conjugation, complex conjugation iota. So let us take sigma to be exactly a complex conjugate of pi, composed with the outer conjugation by iota. And then this bilinear pairing becomes the L2 inner product of phi pi and the right translate by h iota of xi pi. So this is the way that this integral is Eulerian, and for decomposable data, this is what you get. These partial L functions which appear here come from the unramified computation of the local integrals almost everywhere. So you have the L function of pi times tau at s plus 1/2, and at the denominator you have the usual factor which comes from the normalizing factor of the Eisenstein series we used. In this example, this is this product, and you see that it will not cause any problem when we consider poles which are positive, for example. It will stay holomorphic and non-zero there. And the local integrals at the finite set of places as can be controlled as before. So now we start our business. The functorial lift and how do I use the doubling integrals, generalized doubling integrals in this respect. So as before, I start with a given irreducible self-dual cuspidal representation. Now, since I deal with the example of a symplectic group, I continue with this example. So we know that the lift from SP to N goes to the group GL to N plus 1, GN to N plus 1 odd. So I start with tau cuspidal on GL to N plus 1, which is self-dual. The exterior square L function does not have a pole in such a case because 2n plus 1 is odd. So it is the symmetric L function of tau that has a pole at s equals 1. And I assume that the central character is trivial. Okay, so what do I take in the generalized doubling method? My group here is SPM, M that I used before, but now M is 2n. My GLK group is GL2n plus 1, so K is 2n plus 1. And the larger group, H, was SP2MK, M and K, I just wrote them. So here is the first theorem. Consider the Eisenstein series in the that is used in the doubling method, and consider the Fourier coefficient that we apply to the Eisenstein series in the doubling method. So this was the notation. E, the upper psi um to the k minus 1 was my notation for the application of the Fourier coefficient. So the theorem says that this Fourier coefficient of this Eisenstein series has a pole at s equals 1/2. Of course, when you vary the section. If you think of it, this is quite non-trivial. How do you prove such a thing? But luckily, we have the generic descent at hand, and the proof becomes simple. So I start with, I take an irreducible cuspidal generic with respect to appropriate Whittaker character, pi on GA, which lifts to tau. And we know that it exists. I can use the generic descent, which I reviewed before. So once I have such a representation, then of course, since pi lifts to tau, the L function of pi, partial L function of pi times tau at s plus 1/2 is equal to the L function of tau dual, tau is self-dual, times tau at s plus 1/2, and therefore it has a pole at s equals 1/2, right? And then I go back to the global integral of the generalized doubling method, and I see immediately that it has a pole at s equals 1/2 when I substitute appropriate data, because this L function there appears, and the denominator at 1/2 is holomorphic and non-zero. The finite integrals in the finite places, the local integrals at the finite places, I can control by substituting data to make them non-zero and holomorphic. So the conclusion is that the global integral has a pole at s equals 1/2, and the pole comes from the Eisenstein series. Even more, it comes from the Fourier coefficient of the Eisenstein series. So the this Fourier coefficient used in the doubling integrals, generalized doubling integrals, but for this data, G, SPM, M is 2n, tau on GLK, which is GL2n plus 1, and pi lifts to tau, then, okay, I can forget pi. Pi is not mentioned here. So starting with tau, irreducible self-dual cuspidal on GL2n plus 1, forming this Eisenstein series on SP times, 4n plus 2, 4n times 2n plus 1. I substitute M and K. Then it has a pole at s equals 1/2. Let me rephrase it a little differently. we know that this Eisenstein series, the same one, has a pole at s equals 1/2. So let me take the residue. So I can rephrase the last theorem and say that this residue admits the Fourier coefficient with respect to the character, which I denoted psi with, along u m to the k minus 1. In the language of orbits, which correspond to this character, this is the orbit here. But this is, we can say more. This residual Eisenstein series admits this Fourier coefficient. And what can I say about this Fourier coefficient? That it pairs non-trivially as a function of GH with phi pi g times xi pi complex conjugate of h iota. This integral is not identically 0. Now, all I used was that pi lifted to tau. I didn't use the fact that it is generic. So I could say it more generally. If you take any irreducible cuspidal pi on GA which lifts to tau, then this non-trivial L2 pairing exists. That is, you take pi complex conjugate, tensor with pi iota, it pairs the L2 pairing of this tensor product with this Fourier coefficient of the residue of the Eisenstein series at s equals 1/2 is non-trivial. So this defines the new descent, or the descent that is suggested by the global generalized doubling integral. We call it double descent. So this is the space generated, again, as before, by these Fourier coefficients of this residual Eisenstein series at the pole is s equals 1/2. You know, as a function of two variables, GH on G cross G. By the way, the terminology double descent came from, one time when I told Erez Lapid about this, and I asked him a question, and sometimes later he said, David, about this double descent and so on. He mentioned this naturally, and then secretly I decided to borrow this and call it double descent. And one more thing, we could say, for this proof, we used eventually only the fact that the partial L function of pi twisted by tau at s plus 1/2 has a pole at s equals 1/2. So if you take this assumption, again, you get that pi pairs with the double descent of tau. So here is the main theorem of Ginzburg and I about the double descent. So first, it is non-trivial. Actually, we just proved it. Second, it's a cuspidal space. This is very hard. Then it decomposes into a direct sum of irreducible cuspidal representations. It is multiplicity free. And then, as we explained, it has this form. The summands have the form pi complex conjugate, tensor pi iota. And pi varies over a certain set of representations. So each pi in J lifts to tau. And 5, any irreducible cuspidal representation sigma of GA which lifts to tau has a non-trivial L2 pairing with a unique pi in J. Now, there are cases where R2 tells us that we have multiplicity 1, like SO2n plus 1, SP2n. So in these cases, J actually is the full set of representations, cuspidal representations pi, which live to tau, full L packet. So now let me say something about proofs. So as I said, we have already proved that the space of the double descent of tau is non-zero. And we use the generic descent to prove this. Otherwise, it's really, really non-trivial to show that the space double descent of tau is non-zero. Let me skip for a moment the cuspidality and say something about the third part. I will get back to the cuspidality. So in the cuspidality, what we actually prove is that when you consider the double descent in the first variable, so as functions of g with tg1, that this space is cuspidal in the sense that when you apply any constant term along a unipotent radical inside G, you always get zero. So assume we prove that. Then you can decompose into a direct sum of irreducible cuspidal representations this space, which I denote by d upper 1 psi tau. It's a direct sum of irreducible cuspidal representations of pi of G. Now, let us write, following a union of orthonormal bases of coming from each summand, this Fourier coefficient of the residual Eisenstein series. But now take TGH instead of TG1, so you get, a series following this orthonormal basis, which I call phi pi with upper index I. So pi varies in the set J, and I, according to the basis, orthonormal basis coming from pi. And the coefficients are some functions depending on pi, I, and h. But we know how to write alpha pi h, right? You integrate against the complex conjugate. You take the inner product, the L2N inner product with the elements of the orthonormal basis. These are the coefficients. Now we proved in another paper, a much more general theorem, where a special case of that theorem says that this integral viewed as a function of h actually describes an element of the representation pi complex conjugate iota. It lies in that space. So this is a function which I can call xi within the upper index I, coming from the cuspidal representation pi bar iota. And then you get such an expression of this element of the double descent, this Fourier coefficient of the residual Eisenstein series at the pole s equals 1/2. So it exhibits it directly as an element of this direct sum. So now let me talk a little bit about the proof of cuspidality. Of course, I cannot give too many details. It's pretty long. And just to, play with another group, let me switch example and take, instead of the symplectic group SPM, take G SOM and take M to be even as before to M prime. from SOM, from this SOM, the functorial lift to GL goes to GLM. So I take GLK to be GLM, so K is M. And the larger group H, as similar to what we had before, is SO2KM. And the Eisenstein series there, similarly, is induced from the Speh representation delta tau M. But now, since tau is on GL2M prime, and I want it eventually to come to be lifted from SOM, so I assume to begin with that the symmetric square function of tau has a pole at s equals 1. Let me denote by script E with index delta tau M at 1/2 the residual representation of this H of SO2KM, generated by the residues of the Eisenstein series at s equals 1/2. Now, this representation is small in the following sense. If I take one local place where the representation tau is unramified, and I write the local representation tau V as induction from a character of a self-dual character of the Borel subgroup of SO2M prime. So I need M prime characters chi1 up to chi M prime, and then their inverses. And I assume that they are unramified characters of FV star. Then one can check that the factor at this place V of the residual representation at 1/2 is the unramified constituent of the representation written here. So this representation written here is induced from a character of a parabolic with, say, large Levy part. What is the Levy part of this parabolic? Q with this index m+1, m-1 repeated m time. You take, along the diagonal, you take the block matrices GLM+1 and then GLM-1, and you repeat it m prime times. And on each GL block, GLM+1, GLM-1, you take the character of determinant composed with determinant chi1, chi2 up to chi m prime. The unramified constituent of this residual representation lies in this parabolic induction. And this bounds the partitions of 2km, which corresponding to Fourier coefficients that the residual representation script delta tau m 1/2 can admit. And one computes that this bounding partition is given by this partition. And we use this to prove that many Fourier coefficients which come up in the proof of cuspidality, doing all kinds of Fourier expansions, are 0 on the residual representation coming from delta tau m at the pole 1/2. Okay, so trying to prove the cuspidality in the first variable of the double descent, we start with the unipotent radical of a maximal parabolic of G. Recall that G now is an even orthogonal group, SO2M prime. So you take R between 0 and M prime, and let U R with upper index G to remind ourselves which is the group, be the unipotent radical of the parabolic subgroup with Levy part GLR cross SO, the rest, M-2R. And we consider the constant term along UR cross 1 of the double descent. So in the end, we get some nice tower relation. Well, it looks like a tower relation. So we prove that this constant term is non-trivial on the double descent if and only if the Fourier coefficient written here in 5 is non-trivial on the residual representation E script E delta tau M at the pole 1/2. So I need to explain all these notation. So roughly I can say that you take here these residues, EF, the section, of course, you need to vary all the time. Yeah, it's not the same F, it's not the same section which appears when you calculate the constant term. I take a general, I take the section varying. So this upper U 2K minus 1R, if my notation is consistent, you understand that I mean take first the constant term in SO2Km along the unipotent radical U2K minus 1 times R. This is the unipotent radical along the parabolic subgroup with Levy part GL2K minus 1 times R cross SO, whatever you need. It will show up soon. So first, there is some constant term. And this already, you will see, is going to limit R. But as for generalities, I need to further compose with Fourier coefficients with respect to characters on the levy of unipotent radicals on the levy. This first character is coming from a unipotent radical in GL2K minus 1R. And this unipotent character is coming from the smaller orthogonal group in the middle. So here it is inside the brackets, the square brackets. We take the constant term of the residue at S equals 1/2 of the Eisenstein series along this unipotent radical of the parabolic subgroup of SO2MK with this Levy part, isomorphic to GL2K minus 1R times, you compute, so it would be SO2 and inside M minus 2R times K plus R. And outside the bracket, you need to take Fourier coefficient along a unipotent radical inside the Levy part of these two characters. I will write them soon, just for completeness. So the character on the orthogonal part of the Levy part is defined in a similar way to the character which is used in the doubling integrals and is used to define the double descent. Okay. But it is with respect to this orthogonal group and this unipotent radical inside this orthogonal group. But the details are not important. I write it just for completeness. And on the GL part, you take this character. Now, as I said, for the cuspidality, this is not important. What is important is the fact that I take this constant term of the residue. And since I induce from a Speh representation delta tau M and tau is onGL for this constant term to be non-trivial, 2K minus R must be divided by K. K has to divide 2K minus 1 R, because tau is cuspidal on GLK. Okay, so K might divide to K minus 1 times R, and therefore K might divide R. But remember, K is M is to M prime, is the size of my orthogonal group SOM. And R, I took constant terms with respect to unipotent radicals of G, UR. So R is less than M over 2, which is M prime. So R between 0 and M over 2 must be divided by M. So R is 0. So these are the only constant terms that can contribute something non-zero. So this means that this representation is cuspidal. And finally, there is a work to be done to show the unramified correspondence. So I continue with this example. Same group, SOM, M is even, K is M, GLK is GLM, and the larger group is SO2KM. And recall, and I take a place V where tau V is unramified. I write it as parabolic induction from Borel as before. And recall that at V, the unramified component of the residual representation was in this induction here, written here. So what we have to do is to compute the Jacquet module of this parabolic induction with respect to the character psi with index u m to the k minus 1. Let me denote this parabolic induction here inside the Jacquet module by rho chi 1/2. And we prove the theorem that this Jacquet module is isomorphic to this tensor product of parabolic inductions from Borel of G from the character chi1 cross chi2 up to chi m prime. So these representations, they lead to tau v. If you allow me several more minutes, I can say a little more
Please do.
About, more generally that. So more generally, as far as this unramified computation goes, we can show the following. So for functoriality, in this example, for example, of SOM lifting to GLM, so K was M. But now let me take M to be an integer multiple of K. Like M equals 2K, 3K, 4K, mu 0 times K. But tau remains on GLK. And tau remains unramified, coming from this self-dual unramified character of the Borel of GLK. Let me take, again, for this example, K to be even, but you can do all cases. Apply the same Jacquet functor, but with M and K minus 1, and M related to K, M is a multiple of K by mu 0. So before, we had chi j composed with determinant of GLM plus 1 and GLM minus 1. Now replace the 1 with mu 0, with the multiple. It so happens that if you take our Eisenstein series and now you can look at other poles of this Eisenstein series. For functoriality, I looked at the pole s equals 1/2. But it has other poles. For example, this one has a pole at μ0/2. So I can take the residue of this Eisenstein series at this higher pole. And its component and V shares the same unramified component with this parabolic induction written here. So apply the same Jacquet module to this parabolic induction, and we show that this Jacquet module is isomorphic to the following parabolic induction on the same SOM, but now coming from the characters chi1, chi2 up to chi_m prime composed with determinant GL μ0. Let me denote this representation by pi tau mu comma 0. And you can check that this representation, it is unramified. It lifts to the factor of the Speh representation delta tau mu0. So when mu0 was 1, it lifted to tau v. If you take mu0 any positive integer, it's going to lift to the v, the factor at the place v of this Speh representation of tau, of length mu0. Now, it is compatible with the global picture. For example, if we return to the global setup and we take m to be an odd multiple of k, so mu0 now is 2L0 minus 1, and the representation tau, you require that its symmetric square L function has a pole at s equals 1, then we can show that this Eisenstein series has a pole at the point L0 minus 1/2. And we could apply the construction of the double descent to other residues, not only the residue at S1/2. We could apply it to other poles. So when you apply it to this pole, L0 1/2, but now L0 relates m and tau by this requirement that m is the odd multiple to L0 minus 1 of k. And my GL representation, tau is onGLk. So at the unramified level, I just explained, we get the representation pi tau v mu0. Mu0 is 2L0 minus 1, which lifts to the Speh representation of length 2L0 minus 1, corresponding to tau at the place v. So the hope is, or it seems that when you apply the construction of double descent to other poles, if you have the right relation between m coming from the group and k for the GL representation, you should achieve all irreducible automorphic representations of G, which lift to this Speh representation. Now, one non-cuspidal representation you can write down immediately. You take this parabolic induction to SOM of the coming from the parabolic subgroup, well, I hope you got my notation, induced from the Speh representation on the GL part of length L0 minus 1, and here you put the determinant to the power s, times the descent of tau, the generic descent of tau. This, the Eisenstein series here has a pole at L0 over 2, and it lifts to the Speh representation of length 2L0 minus 1 corresponding to tau. If there is a cuspidal representation which lifts to this Speh representation of length 2L0 minus 1, you are going to find it in this descent, double descent corresponding to the pole L0 minus 1/2. So the unramified correspondence shows that at least at this level it works. So there is some extra work to be done here to say, you know, a more clean-cut theorem. Okay, you can say similar thing about the case where M is an even multiple of K, but now you have to ask that to require that the exterior square L function of tau has a pole at s equals 1, and then you get a similar picture with the double descent, but now at the pole s equals L0. Okay, let me not detail this. It's similar to the other case. It's on the slide. So thank you very much.
Thank you very much, David. Questions, please.
Can I ask a question?
Yeah, it sounds like Freydun.
Yeah, it's me.
Yeah. Hi.
When the ordinary descent was done in the, long time ago, before the functoriality, one of the good applications of it was that it would lead to a proof of the L packets having the tempered packet.
Right.
Do you have applications of that sort? You already told us some applications at the very end of the talk. Do you have applications of that sort in your? Do you expect something like that come out? You clearly can say things about the L packets by these last discussions that you told us.
So we played a little bit around. For example, one can ask, okay, you have the double descent. It covers everything which lifts to tau. Can you find a generic representative, show that it exists using this? Can you find some representative in the L packet which has a given model, like a Bessel model or Fourier-Jacobi model? And then the method would be, okay, take the double descent. You have an explicit formula for that, and apply to it Whittaker coefficient, right? And then get some formula that or something that tells you that it is non-zero. And I don't know if surprisingly enough or not, it seems that when you try to compute the Whittaker coefficient of the double descent, you end up somehow at the generic descent. So we think that if you want to, find or give a criterion whether there is a representative with another model, like a Bessel model, that you will end up, when you compute this Bessel coefficient, you will end up with the Rankine-Selberg integrals, which are expressed in terms of the Bessel model, and it would be equivalent, and we are not sure if it's going to give something new. So you either work with the global integrals, which are expressed in terms of these Bessel models, of Fourier-Jacobi models, define the descent using these integrals and find conditions that it is non-zero, that it would be the same as if you do it with double descent. So yeah, I think that at this point, we don't have anything more new to say in this respect, meaning finding distinguished representatives in L packets.
Thank you.
First, to add something, then to ask a question. First, let me just mention. Let me first mention that regarding the Speh representations in the work of Kai Friedberg and myself, the proof that these representations support the unique degenerate Whittaker model in a sense we need was actually Dimel's proof. I sat in his office and he dictated the proof to me.
Oh,
so,
okay.
I'm giving him credit. And I also
so I should add Dima to it. Sorry. Yeah.
And I would also like to ask regarding the size. So you obtain all representations which lift to tau. Is it clear that what the size of the set of these representations is?
I think other people which are more experts than me can say, but isn't this an infinite set? That
yeah, I mean, it's a global thing. So it's an
yeah.
Locally, maybe you can ask locally if there are.
But you haven't written down the local analog, right? It's still
no, but the local analog, is clear that most of it works locally, but you need some basic information to make it solid. But no, we did not write, of course.
Also, if I may, in your work on the Eisenstein, you are using a certain identity that you proved in a separate paper on Eisenstein series, right?
Right.
And in that work, you consider the more general setup where you induce not from a Ziegel, but from GL times a classical group, right?
Right.
So that identity does not play any role here, right?
No, it's only the first case of that identity. I mean, you could view these identities as a tower where the initial case is, the cuspidal representation itself, as you get from the generalized doubling method. And then when you go up the tower, you get these Eisenstein series parabolically induced from a Speh cross a cuspidal on the level. And the Speh is based on one representation tau, but the length of the Speh representation goes up and up and up. So when the length is 0, you get the first part, the bottom part of the tower, and this was the case of the identity which I mentioned before.
If no one is going to ask, then maybe I can ask another question regarding if you can go a bit back to the local, the slide where you talked about unproofs, where you talked about the unramified case. Yeah, just downwards a bit. Yeah. This one. We consider the Jacquet module. Yes. So can you maybe say one or two words regarding that structure? Where does it come from?
Actually, large parts of the proof of unfolding this Jacquet module, if I can say, or decomposing it, bear quite a lot of similarity to the proof of cuspidality in the global case. But otherwise, it's quite long, involved. So you need to do some Mackey theory actually on this induction. And well, it's hard for me to say more, but there are many parts which bear a lot of analogy to the global, say, computation of the constant term that we did on the double descent. Well, the details are in the paper in the archive. No, I cannot say something, you know, descriptive and short about this, but it works really great. That it's rough. It's basically an induced representation, and it's the tensor product of this unramified representation with itself.
Thanks. Thanks.
So, may I ask some question?
Yeah.
So, I'm wondering, using the double descent method, I'm wondering we can all irreducible cuspidal representation of irreducible representation pi, which related to tau.
I'm sorry, I think I did not understand. Can you repeat the question again?
Okay. Using the double descent method, I'm wondering, can we get all irreducible cuspidal representation pi, which related to tau?
Yeah. Well, up to questions of multiplicity. You know, SO2n plus 1, SP2n, how to prove multiplicity 1. So you get all of them, all cuspidal representations appearing in one direct sum, which leads to tau. For SO2n, the multiplicity can be 2, so we have to be careful and just say that this would be up to an isomorphism. So if you have an irreducible cuspidal representation pi which leads to tau, then it will have a unique element in the decomposition of the double descent with which the L2 pairing would be non-zero. So in this sense, it will be isomorphic to a unique representation pi which appears in the decomposition of the double descent.
The representation which gives the non-zero L2 pairing is the one.
What's the question?
The element which gives the non-zero L2 pairing is the original one.
Well, I did not give all details of the proofs. It will take longer time, but I said the decomposition of the double descent is multiplicity free, multiplicity 1. And I said also, I think I explained it actually, if a representation pi lifts to tau, you will see it in the double descent in the sense that pi complex conjugate tensor pi iota will have a non-trivial L2 pairing with double descent.
Yes, thank you.
So it will have to see one summand in the decomposition, and since it is multiplicity 1, it will see a unique sum.
Oh, I see. Thank you.
Can I ask, like, is the multiplicity 1 so coming from like the Jacquet module like calculation, or it's
No, it's actually quite simple. One of the reasons that the global doubling integral is Eulerian, one of the reasons is that the you know, the matrix coefficients are unique, right? So it has to do with this.
Ah, okay. Thanks.
Any further questions? If not, let us thank David again.
Okay, thank you very much. So who is speaking next week?
I think Birgit Speh. Let me check. Yes, indeed, Birgit Speh
Okay.
from Cornell. On, oh, let me say on what. I don't have the title yet. Sorry. So everyone is welcome next week. And I should say, David, I was slightly afraid that some people will be asleep today, but apparently not. We have a very large audience.
How many?
So not now, because now it's after questions, but we used to have more than 40.
Yeah.
Ah,
Yeah.
But by the end of the talk, people got tired of questions, but the talk itself, there was some 40.
I was quite nervous giving this talk. It's my first time giving a talk, you know, from far away, and I'm still quite shaky with using Zoom and all these gadgets.
The day after election in US, that's also.
Huh?
The
Yeah,
day-
what's going on?
Wow.
I think, yeah, today I was preparing for the talk, but I checked the website, news website, maybe 25 times.
Not finished.
You're not done.
Not done.
Yeah, I know that.
Biden is doing fine. That's the.
I'm quite amazed, actually.
What